Welcome to the journey which will take you a ride through the concepts of detection theory. Let us kickstart our journey by introducing my team members. Abhirami S, Bhavani G, Vignesh S, Anjani Kumar, Swami. And here comes the different levels of our journey. First level would consist of introduction to detection theory and different techniques involved in it. And the second level would consist of problem set of detection theory, that is question number 4, 5 and 6. What is detection theory? Detection theory or signal detection theory is a means to quantify the ability to discern between information bearing patterns and random patterns that distract from the information. In the field of electronics, the separation of such patterns from a disguising background is referred to as a signal recovery. According to the theory, there are a number of determiners of how a detecting system will detect a signal and where its threshold levels will be. The theory can explain how changing the threshold will affect the ability to discern, often exposing how adapted the system is to the task, purpose or goal at which it is aimed. Now, the techniques involved in detection theory are the Bayes theory, minimax and the Neyman-Pearson. Now let us see what is Bayes decision rule. Bayes decision theory is a fundamental statistical approach to the problem of pattern classification. It is considered the ideal case in which the probability structure underlying the categories is known perfectly. In Bayes decision theory, the prior probability is fixed and the threshold is calculated, and we always look for the minimum value of the average cost. Now let us see what minimax technique is all about. The Bayes criterion assigns cost to the decisions and assumes knowledge of the prior probabilities. In many situations, we may not have enough information about a prior probability, so Bayes criterion cannot be used. One approach would be to select a value of P1 for which the risk is maximum and then minimize that risk function. This principle of minimizing the maximum average cost for the selected P1 is referred to as minimax criterion. The third technique used in decision theory is the Neyman-Pearson technique. According to Neyman-Pearson technique, the probability of detection is maximum when the probability of false alarm is less than or equal to alpha, where the decision rule is given as follows. Now let us learn how to apply these techniques in order to solve the problems. Here comes our first problem. It is given that P0 of y is equal to 1 by root 2 pi e power minus y square by 2 for y belongs to R, and P1 of y is equal to 1 by 5 for y belongs to 0, 5 and equal to 0 for y does not belong to 0, 5, with pi naught is equal to 3 by 4, pi 1 is equal to 1 by 4 and uniform cost. Our aim is to find out Bayes rule, minimum Bayes risk, minimax rule, minimax risk, Neyman-Pearson rule and probability of false alarm for alpha belongs to 0, 1. From the given specifications, the likelihood ratio is formulated according to the Bayes rule as L of y is equal to 1 by 5 divided by 1 by root 2 pi into e power minus y square by 2 greater than or equal to tau, where tau is given as the ratio of R0 divided by R1, which is equal to 3 in this case. On solving, we have y greater than or equal to 1.89. Therefore, the Bayes rule can be written as gamma of y is equal to 1 for 1.89 less than or equal to y less than 5 and equal to 0 for 0 less than or equal to y less than 1.89. In order to calculate the Bayes risk, we use the cost function equation, which is given as C bar of gamma is equal to pi naught into R naught of gamma plus pi 1 into R1 of gamma. On integrating the density function over appropriate regions, we get the Bayes risk as 0.1165. For the minimax rule, the likelihood ratio is considered as L is equal to P1 of y divided by P0 of y, which is greater than or equal to pi naught divided by 1 minus pi naught. On substituting the equations for P1 of y and P0 of y, we have pi less than or equal to 1 divided by 1 plus 5 divided by root 2 pi into e power y square by 2. At y is equal to 0, we have pi naught is equal to 0.33, and at y is equal to 5, we have pi naught is equal to 0.99. Thus, pi naught is minimum at y is equal to 0. From equation 18, we have pi naught less than or equal to 1 by 1 plus 5 by root 2 pi into e power y square by 2. Now, solving for y to get in terms of pi naught, we have y square is less than or equal to m, where m is equal to 2 ln 5 pi divided by root 2 pi into 1 minus pi naught. Therefore, the minimax rule is given by gamma of y is equal to 1 for 0 less than or equal to pi naught less than 0.33 is equal to root m for 0.33 less than or equal to pi naught less than 0.99 and is equal to 1 for 0.99 less than or equal to pi naught less than or equal to 1. For the calculation of the minimax risk, the condition to be used is R naught of gamma is equal to R1 of gamma, that is, we equate both the cost. Now, R naught of gamma and R1 of gamma are obtained by integrating the density functions over appropriate regions. On solving, we have phi of root m minus phi of 0 is equal to phi minus root m divided by 5, where phi is the Gaussian function. Now, let the solution of this equation be root m is equal to gamma naught. Then, minimax risk is pi l is less than or equal to 1 by 1 plus 5 by root 2 pi into e power y square by 2. The Neyman-Pearson decision rule is given by gamma Neyman-Pearson of y is equal to 1 for root 2 pi divided by 5 into e power y square by 2 greater than or equal to eta is equal to 0 for root 2 pi divided by 5 into e power y square by 2 less than eta. It can be rewritten as gamma np of y is equal to 1 for y greater than or equal to eta dash is equal to 0 for y less than eta dash, where eta dash is equal to root of 2 ln phi eta divided by root 2 pi. There are two cases of regions in this case, which is given by gamma 1 of y is equal to 5 for eta less than 0 is equal to eta dash for eta belongs to 0 to 25.